Hi, everyone. Yeah. Thanks for having me. If I had a nickel for every time I had to fill in for Peter Knight. Um, yeah, so for those who don't know me, Peter Turner, CEO of City Quantum Academy and a member of the quantum engineering group at Macquarie University. So yeah, I'll start off. We'll see if, yeah. My first interaction with John goes back to 2002. It was the early days of my PhD. I was in Toronto. I snuck across the border uninvited to Boston to QCMC, which is being held in Cambridge at the time. Probably many of us remember. And yeah, very new PhD student. I didn't really know anyone in the field at that time, also coming from a different research background. But I remember in Cambridge somewhere, I don't remember the name of the place, we were in some pub and I was talking to the few people that I did know in the field. And I mean, Gavin stole my joke. I had never met John, but I heard John in a room, a pub in Cambridge that was full of physicists at QCMC. You could still hear John well above the noise floor of what was going on. So had many interactions with John in the years, like many of us, in the years following that. I didn't work with John directly, unfortunately, but I just also remember of the many you know, funny evenings and anecdotes with John, being in Tokyo for AQUIS in 2010. I think a few of us were there as well. And we noticed this phenomenon where if you get John Dowling and Jeremy O'Brien interacting, there's some nonlinear thing that goes on. And we were in an izakaya just around the corner from the University of Tokyo. And for those of you who've been in Japan or lived there, it's very, very, very hard to be kicked out of an izakaya. But it's the closest we've ever come was John and Jeremy getting a little bit rowdy down the street from University of Tokyo. So yeah, fun stuff. I'll also just point out something I was very happy to learn. I had no idea. I don't know how many of those of you do as well, but so this is taken from the group theory notes I wrote years and years and years ago, and I had heard about this book that I couldn't find. It didn't even have it in the library in Toronto at the time. And I was happy to learn later on, talking to John, that Barut was John's PhD supervisor. And this book is very special. My PhD supervisor recommended to me to learn some of the detailed stuff that you don't get in other books, and this is what I wrote in my notes. And when I asked John, he's like, "Oh yeah, I know all that stuff." And just to finish it off, another funny story that not really to do with John, but I did find the book in Tokyo. If you're ever in Jimbocho, looking at used bookstop, I was like, "Oh my God, there's that book." I bought this book, and a week later I popped in, and they had replaced it already. So yeah, if you're looking for old textbooks, Jimbocho in Tokyo is the place to go. Anyway, yeah. John will definitely be missed, and again, it's a pleasure to speak here about some stuff that's somewhat related. This is old stuff, so apologies to those in the room who've seen this stuff before. This is work we've done over the last few years around distinguishability in quantum photonics. So I think a bit of motivation. I'm sure a lot of us know this, but bear with me. So the prototypical two-photon quantum interference experiment, as I think most of us are taught, is the Hong-Mandel experiment, where you're sending photons through a beam splitter, and you're changing in this case, the timing degree of freedom of the photons, and you're observing coincidences at the output of this two-port interferometer, right? So and the curve over here is the famous Hom dip, as they call it. When the interferometer is aligned, you see that coincidences go to zero, which is this hailed as this purely quantum effect, non-classically explainable. And then when the timing degree of freedom makes the particles distinguishable, you get this constant coincident count rate. So this is kind of the workhorse of much, you can imagine, much more complicated linear optical experiments, and one direction this goes is something I'm sure we've all heard of, boson sampling, where you're going to put lots of these non-interacting bosons, preferably indistinguishable, into a random linear network, and there are these amazing results. And Aronson and Arkhipov and whole community now that exact sampling is hard unless the polynomial hierarchy collapses, and then even approximate sampling is hard, assuming some reasonable conjectures around matrix permanence. So this is driven. This is looked at, if you like, as a kind of analog quantum computation. You could think of it that way. And there's been, this requires very large interferometers and lots of photons. And integrated photonics is the way that this is starting to become a reality. And this is an example of a 6-mode device from Bristol many years ago. We know that nowadays integrated photonics has become a multi-$100 million investment opportunity for some of us sitting over there. So there's a lot of effort going into scaling this thing up, and we've seen results. And I mean, this one isn't integrated, but Barry's here from last year on some of the boson sampling quantum computational supremacy demonstrations that have taken place over the last few years. So become quite a hot field. And for those probably those in the field certainly know, and others can guess, the kind of two major error processes for these linear optics processes are loss being one of the main ones, and then distinguishability being kind of the next one down the list. So I'm going to talk about modeling distinguishability in quantum photonics and these multi-boson, multi-mode big experiments. So the model is really embarrassingly simple. I'm just going to put an extra label on a creation operator, and you can argue, you know, the interpretation of this. But I mean, in any fixed number of photon experiment, you know, this can be used to describe what's going on, and I'll show you how to do that. The reason we want to do this is basically I want to the direction we're going is that I want to go to kind of a first quantized quantum information type of approach to this question, and I'll argue why you can't do that easily in second quantization, and show you how to do it. So first of all, when I'm indexing these things with two indices now, I hope you'll forgive me. I'm going to write my Fock states as arrays, and that's because it's easy for me to see that if I've got this interferometer now. My 1 and 2 are the two spatial modes, say, in this interferometer, and the columns are now this distinguishing degree of freedom, whatever it is in this case. I guess I've written it as polarization. So that's an example of an indistinguishable state of two photons in two modes in this formalism, if you like. Is that all right? Sorry? Love it? Oh, good. Yeah. Yeah. And then, of course, a distinguishable state, a completely distinguishable state. A completely distinguishable state, for example, would be this one, saying I'm going to put an H photon in the top and a V photon in the bottom. Is that all right? Okay. So probably be boring for a lot of I know there's a lot of experts who know a lot of this stuff probably much better than I do. Maybe as a fun exercise, and in honor of John, something that looks a little bit like a noon state. I guess a question for people to play with is that, would you call that state the superposition of these two entirely classical situations, distinguishable or indistinguishable? So you can think about that if you like, and ignore as I go through this formalism. Sorry, the second quantization and first quantization. So I said this is where we were going. Reminder, second quantization. The systems, the Hilbert spaces are modes, infinite dimensional Hilbert spaces, simple harmonic oscillators. The states are particles, or I'm keeping track of how many occupations are in these modes. And the unitary action of a linear optical network, for example, is kind of automatically symmetrized by the fact that I'm working with the operators and not the states, and the operators, the ring of operators commutes and off we go. And this is undergraduate stuff, maybe part of the major reason that we're taught second quantization in undergraduate. And then in first quantization, which is where most of us do quantum information research, the systems are particles, so our Hilbert spaces are particles, and the states are modes, if you like. I'm particle 1 and I'm in mode H or something like that, right? And we've got to go in, as we've also learned in undergrad, but now I've got to go in and symmetrize these things by hand. these are bosons, I'm assuming. And of course, anti-symmetrize them if they're fermions. And I've got to symmetrize the entire wave function again, as we learned. And now the unitary action, it's transversal. If you think of this as a circuit in quantum information picture, every photon sees the same unitary. So it's just U down the line, if you like. If I'm thinking about a quantum optics experiment now as a circuit. Is that all right? But there's been this highly non-trivial symmetrization element to the circuit that nature has done for us, if you like. Is that all right? Okay. So in general, I can now generalize. So that this model is, I mean, part of the reason this model is completely general and it's exact, so it can only get you so far. The complexity is going to be there. In general, I can think about DS system modes and DL label modes for n particles. And the Hilbert spaces, the tensor product in the Hilbert spaces, this is in the second quantization, of course. I've got these harmonic oscillators, which I'm just writing as C infinity. And I've got DS times DL of these things. This is the number of entries in those Fock arrays that I was writing down. And of course, that doesn't have a nice system label, if you like, tensor product structure that we would want from a quantum information perspective. Because again, I want to focus on the system and I want to trace out this label in the long run. So first quantization, as we've said, it's just formalizing what we've just said in words. I've got n particles. They've each got a number of system states space, and they've got a certain DL dimensional label state space. And I'm looking at this symmetric product of these Hilbert spaces. And the key to all of this is something that's been known for a long time in other fields, in maybe mathematical end of many body physics. But this has this Hilbert space, this symmetric Hilbert space has a decomposition. It's called unitary duality in some language. And this is again just notation, but basically this is the sum over irrefs of the unitary group on the system, if you like, Hilbert spaces, and the unitary group acting on the label Hilbert spaces. And I'll show examples of this in a second. So really, this whole formalism is really just kind of observing this fact and studying what it means in linear optics, if you like. So just to go through that procedure in detail, it's probably helpful for the simplest example. Here's that Hongel-Mandel 2-photon 2-mode indistinguishable state, we called it. So now in first quantization, I've got to symmetrize, photon. I've got these fictitious particle labels 1 and 2, which I'll get rid of in a moment. Say photon 1 is in the top first mode and it's H, and photon 2 is in the second mode and it's H. I've got to symmetrize it. Of course, it's the second line. Then I just rearrange the tensor product structure, which of course I'm allowed to do. I want to separate the system from the label. That's just commuting of Hilbert spaces in the tensor product. That's no problem. And then I'm going to write that. This is hopefully obviously that's a symmetric combination of these two things. And so is that. I'm going to write this in this group theory language just because it does make things a bit shorter. I mean, I know it annoys some people. I passed a draft of a paper around years ago in Bristol, and the experimentalists came back and said, your latex fonts are wrong. But it is a nice compact notation. This is just that state, and this is just that state, this symmetric. If you like, it's a 2-mode problem. This is the m equals 0 state, if you like, of the quantum numbers 1 and 2. And this is an m equals 1 state, say, of the particle, the quantum numbers HH. Yeah.
How do you distinguish between the symmetric and antisymmetric? Because you could have two antisymmetric.
Yeah. So thank you, Peter. There you go. All right. So do the same. That was great. We didn't even set this up beforehand. That was the indistinguishable case, and now the distinguishable case. You can do exactly the same procedure. You do it on a few lines, and if you'll trust me, you get this thing. So that unitary duality, you can kind of see it here as quantum information theorists. We're like, that's a separable state. That's, this is Schmidt number 1. That's Schmidt number 2. This unitary duality it's like a Schmidt decomposition for this symmetric space of n particles with more than 1 degree of freedom, if you like, or 2 degrees of freedom in this case. And this is the antisymmetric combination of these quantum numbers, as Peter was nice enough to anticipate for us. So the lesson there, if you like, distinguishable states. If you, again, thinking kind of as quantum information people in a language, hopefully not too misleading, it's like, okay, distinguishable photons, it's like they've got an eavesdropping degree of freedom that's on the photon, the particle itself. And that eavesdropper, if you like, is we can trace out the second degree of freedom that say our detectors are not sensitive to this polarization degree of freedom in this game. Oh, sorry, by the way, of course, I changed the HOM distinguishing degree of freedom from timing to polarization, but hopefully everyone's comfortable that it's the same argument. And I'm going to get mixed states, and you can do that, and you can go through and analyze Hom. You could write down the matrices. You could do whatever. I didn't write down the density matrices. I hope most of us can just see, of course, that this is. I'm going to trace out. This is going to give me a pure state. This is going to give me a mixed state. And then, as all of us, certainly in this field, are now very familiar with, the dynamics of in the symmetric sector, if you like, of this part of the wave function evolves according to the permanence of the unitary matrix that defines my linear optical network. And this has been made famous in the last 10 or 15 years around the boson sampling, but it goes back to Stefan Schell, and Terry mentioned it to me many years ago, and it goes back in the combinatorial community even further. What's maybe a little bit less known is that, but not maybe surprising, is that for the antisymmetric sector, this wave function, this part of the wave function is going to evolve according to the determinant of the unitary that defines the linear optical network. And of course, if you think for a second, if I've got any 2x2 unitary, its determinant, or at least the absolute value of its determinant, is going to be 1. So that this part of my wave function is going to give me coincidence counts no matter what. In fact, no matter what interferometer I put it through. Whereas this one, I can pick interferometers that make the permanent go to 0, such as the 50-50 beam splitter. In fact, the only, up to phase, the only interferometer that's going to kill that term. So basically, here's a first quantized, if you like, analysis of the Hom situation. And the point, of course, is that this is completely general. I can now do this for any number of photons, bosons. I could do fermions if I wanted to do the antisymmetric version of this in any number of modes. And again, I'd use this group theory language. Now things I'm not going to write n boxes in these Young tableau type of things, but this is the same kind of thing. So here's a basis for that space, a basis for that decomposition that I wrote down a few slides ago, the unitary. There's a Schur-Weil decomposition if you use that language. This is the EREP. This is what I call the outer multiplicity. Here's your occupation number. And there's something called an inner multiplicity as well. It gets pretty complicated in the general case. It leads to some interesting stuff. And the same thing for the label. And in fact, this is one way you can prove the unitary decomposition. If you're given the Schur-Weil decomposition, I just do 2 of them and couple them. And now I can cook up states. I can ask myself. Sorry. Here's an example. Again, if you're playing around with 2 particles in 4 modes, which was what we started with in the Hom case, or if you know the expression for that, there's 10 states. And here's exactly what's happening. 9 of them are a triplet coupled to a triplet, so that's 9 states. And the last one's a singlet coupled to a singlet. So there's your 10 states. So I've proved, I've done dimension counting on one example. Maybe you'll believe that it's true in general. And then you can, and then as we've already seen, an example of an indistinguishable state is exactly this kind of thing. And now I can say, oh well, now I've got I can cook up all sorts of different types of what I would call an indistinguishable state. I just need some separable combination of these types of things. I could write down that one, where I've only just changed to V in the second slot of the label degree of freedom. And for those of you who were doing the homework as I was talking, that's exactly this Noon type state that I encourage you to think about at the beginning. So, maybe I've argued that this state is just as quantum as that state. I think in a lot of, it's certainly, as far as the interferometer is concerned, it's identical. These are exactly the same state. It's separable. So there's an argument for why this superposition of 2 totally classical situations is just as quantum as the classical ideal Hom situation. Now things get messy when you've got more particles, but the theme is still there. So I can introduce this kind of distinguishability, partial distinguishability. I can imagine doing that in situations with many more particles, and play this game and do this analysis and see what's going on. So we've done a bit of this. This is work that goes back several years now. This is work with Stasius Stanisic, where one thing you see is you say, oh, I'm going to do this tracing. I'm going to do this quantum information approach to the Hongel-Mandel experiment. It's clear now that Hongel-Mandel experiment is a mixed state discrimination protocol. And I can go through and just do this for as many photons and as many modes as Stasic can possibly do numerically, which I could never do. And you find you get different optimal distinguishing interferometers for different distinguishable states. You might have, one of your photons is different than all the rest, or you might try to be distinguishing the completely classical state from the ideal case, and you can go through and do that analysis. Interesting results there is that the quantum Fourier transform is the best we know of for, oh gosh, I've forgotten now, for a singly distinguishable particle. So you've got one bad photon, say, in your n photon ensemble or input. But it turns out if you're trying to distinguish the classical state from the ideal quantum state, there's a much simpler, lower depth interferometer that does it. And it's kind of not surprising. It should be easier in some sense to distinguish that classical state from an ideal quantum, from the ideal home state. You can do things like, this also showed you, okay, now I really do have a very concrete example of a quantum computation that does boson sampling. So of course we know that's possible. Why would you want to do that? But it's the Schur transform, which we know is efficiently, there's an efficient circuit implementation on a quantum computer. And you can even model boson sampling with loss and now this distinguishability part. So the loss would just be tracing out lines on this circuit. I'm losing particles. And distinguishability would be tracing out this other register with this label register, if you like, of these particles and seeing that decoheres the quantum computation. It gives you a way to do, if you like, some sort of correction or filtering on this. I would, if you were doing this on a quantum computer, and of course, why you would do that, I don't know. But you'd be post-selecting on getting just the symmetric output out of the Schur transform. All this noisy stuff you just get rid of. And it also leads to, you can use this kind of first quantized approach in classical simulation of noisy boson sampling, which a lot of work has been done in the last few years on classical protocols for doing that kind of thing. So again, this is work that's a few years old now. So it's a fun formalism. I mean, the idea was hopefully back in the day that we could actually, that argument about why, this superposition of two entirely classical situations is just as quantum, at least in terms of this argument, as the properly quantum case. Can we harness this? Can we turn this distinguishability bug into a feature? So I'm going to speculate now for a little while on some observations around here. But I think, I mean, just to get ahead of it, in the end, I guess what I've learned is that engineering perfectly indistinguishable inputs is probably as hard as engineering specific partially distinguishable inputs into these kinds of experiments. But still, there's fun stuff going on. I've kind of danced around this, but for those of you who this probably was made famous in the Aronson ArcPub paper, like I say, it goes back before. When I heard this connection between permanence and linear optics, I think a lot of people thought computationally, like kind of complexity theory, oh yeah, this is great. I just immediately said, I've never seen that construction of the symmetric representation of the unitary group before. That's amazing. That's not in any of the group theory textbooks that I know. And immediately I asked, okay, how do I do this for irreps that aren't the symmetric irrep of the group? And you're led to this thing called immanence. And Hubert-de-Guise and Barry and others have worked in this space on how distinguishability. So it's just generalizing that Hom thing. As distinguishability creeps into your experiment, you're getting signal from other irreps down this chain. And there's a lot of results there's not a lot of results in. So first of all, another difficulty with this is that the complexity of construction group representations is not as well studied as I would hope, and maybe you would hope. And I think the answer is basically, as soon as you ask for matrix elements to a mathematician, they just turn off. They're like, that's a basis dependent concept. I don't care. So whereas the physicists, we care about these things. So, there's an outstanding question about exactly how do I get an expression that's as nice as that for the matrix elements of the symmetric representation for the others. There's some things you can show, I'll mention, but anyway, another thing you can ask, and this is work with Alex Jones, who's at the University of Bristol, how do I access, so basically, sorry, what I've just argued, what this formalism shows is that the problem of boson sampling is also the problem of sampling from the symmetric representation of the unitary group. Same problem. So then I can ask, what is the complexity of sampling from other representations of the unitary group? And I start going down this chain. And there is work on the complexity of that, but as I've just said, it's not as complete as you would like. But I can also, we can access these irreps now by cooking up interesting Fock states. So here's an example of a Fock state of 3 photons in 2 spatial modes and say 2 label modes using these arrays. I claim, and you can check, that wave function has this mixed symmetry, if you like. It's remember, it's totally bosonic in the long run. Of course, it has to be. But in each of the 2 parts, the system and the label, it has this mixed symmetry. It's neither symmetric or antisymmetric. And some people in photonics have done this kind of thing, claiming to show transitions between bosonic and fermionic behavior and whatnot. But you can just play this game. You can cook up these things and access these irreps. And there are complexity results that say that accessing these immanent type matrix functions is just as hard as accessing the permanent. So there's a kind of computational supremacy game that can be played there. There's other fun things, and I'm trying to, me being me, I just play off. I just want to understand the math of all this stuff. You can leverage the Fock array symmetry. So this way of writing Fock states, which I found easier for myself to keep track of. There's some meaningfulness in it. So here's a situation where I've got 3 photons in 3 modes, and I ask myself, okay, how do I construct a bunch of Fock states that gives me the antisymmetric sector of this game? And if you look at that, this might be the first thing you'd guess if you just looked at this and I didn't tell you that they were Fock arrays. You might guess that linear combination because these 3x3 matrices are the defining representation of S3, the permutation group on 3 things. Even though nothing's being permuted here, these are just keeping track of occupations of Fock states. So there's something going on in how you could construct these things that I also find quite fascinating. Anyway, what else did I have? I think there's one more interesting, possibly interesting idea here, and as probably those who are in the boson sampling field know, that verification of boson sampling is a huge question. And there's one thing you noticed that I thought might have something to do with it. Again, I'm speculating here. But again, think about 3 particles in 2x2 modes. In the Young tableau, so just think of 3 qubits for a second. In the Young tableau notation, if I tensor 3 copies of spin 1/2 together, oh, sorry, I think I do it I think I write down the angular momentum language that we're much more familiar with. I get a copy of the spin 3/2 irrep, and I get 2 copies of the spin 1/2 irrep. So I think people who play with qubits are probably familiar with that. But now I think about this from this sampling and this matrix thing, right? I had a 3 photonic. Think about accessing these things in this game that I've been talking about. This is a degree 3 polynomial. These matrix elements are degree 3 polynomials in the defining matrix of the interferometer. But I know that if I were to be able to cook up a state that, like I just wrote down, that only lives in this thing, it's going to scatter as this representation. But that's not a degree 3 polynomial. I know that's the spin 1/2 representation. It's the representation I started with. So there's a collapse, if you like, of these matrix functions in certain instances, and the representation theory can tell you where they are. And you can just do that calculation explicitly. So I'm gonna compute the matrix elements in this irrep, this mixed symmetry irrep, which I've just said you could do, this linear optics, you could imagine cooking something like this up. It should be a degree 3 polynomial, and it actually turns out to be proportional to an immanent, and I can compute that immanent, and here's your degree 3 polynomial. It's U11 times a determinant, which is a degree 2 polynomial. But of course, the determinant for a unitary, its absolute value just drops out. So there's your spin 1/2 coming out of it, right? So here's the matrix polynomial calculation that this angular momentum type of thing from our undergraduate textbook predicts. So I'm wondering whether this could be, how this would happen generally in huge irreps of the unitary group. I could imagine cooking up partially distinguishable states, and the complexity of that matrix element should collapse. So that's a question out there. Now, the problem is that in the boson sampling, and this actually might connect to the complexity theory, which I don't understand. In the boson sampling case, you've got lots and lots of modes and fewer photons. And you don't see this kind of you won't reach these kind of irreps if you normally see that. So that actually might tie that, why you need n photons and m squared modes to see boson sampling. But I certainly never seen it analyzed like that before. I don't know what I've got in terms of time, but I was just, sorry. Oh wow. Okay, I'll be done early. I was just going to rattle off a few other interesting mathematical observations in case you weren't asleep yet. There's just all sorts of interesting things going on here. So the other thing you notice is that I don't know how aware I don't know if the combinatorialists are aware of this kind of thing. So the sum over irreps of the mod squares of the matrix elements of the unitary group is equal to a permanent of the matrix of mod squares. And the proof in this case is by physics. If I put distinguishable particles through an interferometer, I don't need, the quantum interference doesn't happen. I just, and then I think it's even in the Aronson Arkhipov paper, I don't have to take the permanent of this matrix of complex numbers. I get to take the absolute values of that matrix, and then I take the permanent, yeah? But as this analysis has just showed, that must be equal to the complete, the addition of a complete chain of all the irreps, because that's, sorry, I only showed it for 2 photons, but for n photons, the completely distinguishable state is a superposition of all the irreps. And so this is saying a very non-trivial mathematical thing. If I want to sum up the permanence or the immanence, the matrix elements squared over all the irreps of the unitary group, it's equal to the permanent of the absolute value squared of the thing that I started with. So again, interesting mathematical fact I've never seen written down. I'm not even sure. Again, if a lot of mathematicians again they don't care about matrix elements, so maybe they don't see these kinds of things. You can generalize mathematical results for existential constant and immanence, which is not too hard to do. You can I said things get more complicated when you've got more particles. You can see exactly where in this model I don't want to go backwards because the clicker's a little laggy, but in that general expression I had, there was that sum over P over the outer multiplicities, as I called them, for these states. That sum is going to give you decoherence when you trace out that second degree of freedom. It's like a max, there's entanglement there because of that sum. So you can see this model shows you where this kind of, if you like, fundamental decoherence of distinguishability gets introduced by again introducing these different irreps and the entanglement across it. You can analyze that exactly. You can see exactly how that comes about. I mentioned this one already. This was the 3x3 matrices, and you're kind of seeing these Fock arrays might actually be useful for just as a guide for guessing, okay, which combinations of Fock states are going to have the symmetries that I may or may not want to explore. And finally, there's a connection to something called contingency matrices, which again I learned about. So if you step back from this and you don't like group theory, which I think the vast majority of people don't, you can say, I don't need to do any of this. You've written down a ds by dl Fock number of harmonic oscillators. I can just do permanence on that huge number of, I can just think of them as bosons on that big number of modes. But if you're going to do that, you need to be able to answer the following question. You need to say, okay, what's my input state? How many photons are in what are the row sums of that Fock array? And then for a specific output, I need to think about the column sums. That's the number of particles I see in each of these columns. And then in order to get the decoherence right, I've got to sum over all of those things. So the problem of, I had to look, I just stumbled across this, been going through this stuff. That's called a contingency matrix. If I give you the row sums and the column sums and ask you how many, not even ask you what they are, how many matrices satisfy, matrices of integers satisfy that row sum and that column sum, I am told that that isn't just P-sharp hard, that's P-sharp complete. So there seems to and then of course you have to do permanence after that if you were going to do the second quantized approach to this kind of thing. So I guess I'm arguing that the first quantized approach is what you want to do here. Secondly, there's so much complexity theory in there that it feels like this around verification and stuff like that, there might be some very interesting questions to pursue. So I think that's the end of my list of rantings and speculations. Renee, reminded me, I should remind all of you that I have a day job. And Quantum Australia is coming up the end of next month, and there are early bird tickets still available. So please, if you're in Australia or going to be in Australia, please think of joining us. And I guess with that, I'll say thanks very much. Barry.
Yeah, very nice. The part about the mathematical game, I find especially interesting because, like you said, it can be very hard to verify both.
Mhm.
The mathematical goodies is probably where we should be looking to be able to design tests, essentially looking at conservation, whatever principles can be satisfied. And I just wondered what your thoughts, but the way you present it, it could be valuable.
Yeah, and that's, I mean, this is really as far as I got. The only one I've thought a little bit more about was that collapse of the complexity thing, where if in the case of 3 spin 1/2 particles, if the fundamental rep shows up in your decomposition and your input state has overlap in that state, in that irrep, I don't need to do any more calculation. I know exactly what the matrix elements, I know exactly what the scattering amplitudes of that thing are. So it feels like there's a verification protocol in there, but I haven't really sat down to think it through. As I said, that I did get as far as thinking, wait a second, boson sampling, you've got few particles in lots and lots of modes, in which case you don't reach down to the fundamental irrep. In your decomposition, the fundamental doesn't show up. And so I think there's actually a connection between the fact that you need, as Aronson and Arkwat show, the fact that you need lots and lots of modes with a fewer number of photons, I think is probably related to that. But there are other, the contingency matrix one, I feel like there's some stuff to be explored there, but it's all just speculation at this point. Gavin, and then I think Andrew.
Yeah, so there's some recent work that shows that you can efficiently classically approximate the output published usage for coarse grain boson sampling, where you just like imagine that
Yeah.
set of detectors and you can't resolve individual modes. You actually kind of have a
Yeah.
that works by estimating those characteristics. So do you think that there's a way to analyze that, make use of permutation symmetry with modes in?
Yeah. So it's another thing that Tim, I think it was one of your students was here recently, and we were talking about something related to this. The idea of coarse graining sorry, I forgot to repeat questions. The question was about, let me just simplify it to say the question was about coarse graining these kinds of things and binning, if you like, the outputs of these. I mean, yeah, that's a very good one. And it comes up naturally. I don't understand the mathematics of it so well. It reminds me, there was another approach to verification, Barry, that Hubert talked about ages ago, which is not binning the outputs, but just separating them off, just saying, I'm only going to look at the output from a subset of the output modes and think about a subgroup structure, some sort of subgroup chain that would take me from the full unitary group on D modes down to the D prime modes that I'm looking at. And you could think about using techniques like this to get into something like that. But the coarse graining one is tougher to me. It's something I'd like to understand better. Yes.
So two related questions. One is just one is really a question for you.
Okay.
So first is about the whole question about the complexity in the case where you have distinguishability, because you were kind of hinting at the fact that if you know exactly what the distinguishability is, then that's maybe equally complex.
Yeah. Well, sorry. Yeah, that's the first clarification question. Yeah.
So I had something like
Yeah.
timing. My distinguishability was the timing of a wave packet of photon. That at some point there's a distinguishable photon.
Yeah.
So what's the trick there? Is
Yeah. The trick, if I've understood correctly, the trick around that is these superpositions. So if I had, so one of the routes to simulating noisy boson sampling is to say, if I've got, epsilon distinguishability in some measure, I'm going to take n times epsilon of my photons in this whole experiment and treat them classically. And that's a fairly standard approach to this kind of thing. But it's been shown, Shishnovich has shown recently that you can efficiently, he claims you can efficiently distinguish classically the outputs of noisy boson sampling from those types of simulations. So there is, and I think this goes to my argument about the superposition of these two classically distinguishable things really is, I would argue, as quantum in the way that I did here as the ideal case. So obviously if you just have a Fock state with certain distinguishability, yeah, you can treat those particles separately from there's no quantum interference. But when you start taking superpositions of such things, you get all the quantum goodness, I would argue, what I'm trying to argue here, or at least a lot of it. And this goes to we know that if by doing that, so to just repeat the argument, we know by cooking up these superpositions of partially distinguishable situations, I start accessing these other irreps. And we also know that the matrix elements of those scatterings are immanents or related to linear combinations of immanents. And unless those immanents are very near the antisymmetric case, they are conjectured to be sharp hard. Yeah.
So, and the follow-up and the question is the way in which you might use theoretical formalism to understand that, or do you expect that there might be some kind of threshold for how much noise could I tolerate, after which forget it, this thing is not one.
So this was the first question I asked I forgot, I mentioned Stasia, who did the discrimination protocol stuff. Alex Moylet was my other student in Bristol, who we started with exactly that question. I should just see, and Andrew, I haven't forgotten you had a question. Maybe this was related to yours because you're smiling. It was exactly that question. It's saying I now have a formalism where I can just dial up the distinguishability in some measure, and I should see some sort of transition from some sharp hard situation to otherwise. Yeah, this shows how you would do that. We never got as far as really laying all that out. And I think a lot of these boson sampling classical simulators are making use of essentially this kind of thing. As I said, they can split off a certain fraction of these things, and they have these curves, and we've done them as well. I flashed a few of them up where you can say, okay, this thing's no longer hard. But yeah, that was an original motivation for one of the things we could look at this one. Andrew, did you still have one?
Yeah, I think so. I was going to ask you about I know it's that's good. I suppose one question would be how often I had very
Yeah, no, so certainly not yet, because going down this route will definitely lead you to the imminent question, and it's not the complexity of this imminent stuff is not that well known. As I said, my understanding of the latest situation is that if you have a constant number of boxes off the antisymmetric Young tableau, then it is simulatable. But other than that, we don't know. That's my understanding of the latest. So it's hard, there's not a lot of granularity as you go up this massive chain of irreps in the decomposition.